Hi, in this video we will be discussing different properties of discrete Fourier transforms. Okay, you have seen discrete time Fourier transforms, and the properties of DFT are very similar to the properties of DTFT. Just that DFT is applied to a finite length xn, assuming that it repeats periodically, right? We have just a finite length xn. We apply our Fourier transforms. As you remember, x of k is equal to summation x of n e to the power minus j omega n, where omega is discrete, 2 pi k upon capital N, where this capital N is chosen by u times n, and this n is not from minus infinity to plus infinity, but it is only from 0 to n minus 1. Basically, it is only over one period, right? So this is simply DFT. Now, how do you assume that x of n is repeating? So if x of n is a long sequence, basically x of n is of length less than or equal to capital N, and then you assume that x tilde n, which is the periodic version of xn, this is the periodic version. So this is true for n equal to n belonging to z, right? Whereas this one is true only for equal to 0 to n minus 1, right? So how do you represent it? So this is how you do it. This is non-zero for only this value and 0 otherwise. So your x is non-zero only for these n's and 0 otherwise, but x tilde n is non-zero for all these n's, which means that it is basically repeating version of xn. And you can equivalently write it like this: x tilde n is x of n modulo capital N, and this is the representation. So very important that I am concerned only with the values of xn in the interval n lying between 0 to n minus 1. And if n lies outside this interval, you take a modulo and bring it back to that interval. This is very important. Bring n back to the interval 0 to n minus 1, right? Okay, now one property of DFT is linearity. As you have seen, x of k is simply e to the power summation over x of n e to the power minus j 2 pi k upon capital N times small n, and n goes from 0 to n minus 1. You see this is a linear thing, so this part, if you replace it with a1 x1 and plus a2 x2n, it linearly distributes, which means you can write this as a1 x1k. Basically this thing is proved, right? So linearity is very easy to see. Next property, okay, now please pay attention. This property is circular time shift. If I want to shift my x of n by some n naught, a given delay or shift n naught also is an integer, what do we get? So what is the shifted version of xn? Okay, let's look at the figure. This will help us to also understand how we actually construct, or how we understand this whole thing. So x of n, it lies between 0 to capital N, 0 to capital N minus 1. Let us say this sequence is of length 4. So from xn, you can construct x tilde n, which is periodically repeating version, right? Let's say my xn is from 0 to 3 only. right? And x tilde n is the periodically repeating version of xn. Now you apply the time shift on x tilde n. What will you get? So in this case, you see this. So your n naught is -1, right? And the whole thing gets shifted. So this is the 0 now. This was the 0 earlier. So the whole thing is shifted towards right by 1, right? But now you look at the interval 0 to n-1. This is my n-1 now. If you just look at this interval, what do you get? You get your x n plus 1 modulo 4. So this is your shifted version of xn, 0 n minus 1. So what you find actually happening is this, the value 2 has gone to 0, this has gone here, this has gone here, and this one has gone all the way in a circular shift. It has gone to n minus 1. So this is something important, right? So basically, it's like a periodic boundary. This boundary is connected with this boundary. Let me write down the term periodic boundary. Okay, next, if I do this circular time shift, basically I shift n by a delay n naught, then what do I get? Then what do I get in the DFT? What is it? How does the transform change? So my proposition is that the transform changes like this. This is how also we saw in DTFT, the transform changes like this. But can we prove that? Okay, let's look at the proof now. So, okay, let's start from the basic definition of xk. So now my x dash k, which is the DFT of this thing, x dash k is DFT of this. Just the formula, nothing special. Now, I want to replace this n minus n naught by some m, so that basically I want to represent my x dash k in terms of x of k, right? So towards that, I'm transforming my n minus n naught to m. So how does the formula change? Very simple. My limits will change from minus n naught to n minus 1 minus n naught, and here it is m. Here n is replaced by m plus n naught, right? So these are some things where we actually see the change. Now let us split this summation into two parts. One part which lies within the interval 0 to n minus 1, one part which lies outside the interval. Now our task is to bring the part which lies outside the interval to inside the interval. Okay, how do we do that? So basically I repeat, I'm writing the whole thing again, nothing has changed. Now let us look at this term. And here I want to bring it back to the interval 1 to n plus 1 and minus 1. So what I have done is I replace m with n plus capital N, right? Just to bring it back. So this term becomes, so this is only this term. This term becomes, now n goes from n minus n naught to n minus 1, and x of this thing, and e to the power this thing. Now you look at this term, this is same as x of n, because capital N modulo capital N will be taken away, nothing will remain. Look at the second term now. Again, e to the power minus j2 pi k upon capital N times capital N will be simply 1, right? So that is why I can ignore this. So this capital N goes away, this capital N goes away. So finally, if I put back, it is this form is same as this form, so I can just merge the two limits. M goes from 0 to n minus 1, this whole thing. Now let us analyze this. So this is xk, so this part is basically x of k times e to the power minus j 2 pi k upon capital N naught. Right? This is what we had to prove. hence proved. So basically in this, you just need to remember that you have to take a circular shift. Basically your x of n is the boundaries are connected. So which means x of n, if you shift from one side, if it goes out, it comes back in from the other side. Right? If it goes out from one side, it comes back in from the other side. Okay. So next property is duality. Let's consider what is duality. Both xn and xk are sequences of length n, right? And I know if I take a DFT of xn, I get capital Xk. But what if I apply DFT on this sequence? Let's consider this sequence as x of n. Apply a DFT. I should get something similar to x of k, small x of k, but what is that? Let us derive. So proof. So proposition is that if I apply DFT on the Fourier transform sequence, then I get back the original time domain sequence, but with the time reversal and a scaling. So time reversal and a scaling. Okay, the proof. Proof is simple. I want to compute this term, which is x dash of k, let us say, and x dash of k is the Fourier transform of capital Xn. This is what I have written here, capital Xn. Now, you know that this capital Xn is basically the Fourier transform of small x of some index m, let us say. So x of n is small xm Fourier transform. So substitute this value here, and what you get is, okay, what you get is this thing. Right, just substitution. Now again, move the limits. M can go out and n can come in, and this is what you get. So if I take out the m limit here and n limit I bring back in here, what I get is this term combined together to form this term, and you know what is the sum of this term, right? K plus m is some constant, for some k plus m constant, you are summing over the small n. And you know that this sum is 0 if k plus m is not 0. If k plus m turns out to be 0, then this sum will, all terms will be 1. So sum over 1's n times, so which is capital N. So basically this term is capital N times delta k plus m. So if k plus m is 0, the sum is capital N. If k plus m is non-zero, then the sum is 0. Right? So simply this. Now if I combine these two, so you are summing over a delta function. So which means when k plus m is equal to 0 means m is minus k, then this is minus k, then you get a single term. So x of minus k, since so I have to remember this modulo thing, because actually you can put this modulo thing everywhere, right? You can put it everywhere. So that is the tricky part with the DFT. So that is what we had to prove, hence proved. Okay, now time reversal. We have already seen some form of time reversal, but let's look at time reversal in a little bit more detail. If we flip the time axis of xn, what do we get? You remember it is a periodic signal, things go out from one end, come back in from the other end. Okay, let's pictorially see it. X of n is simply a length 4 signal. I reconstruct x tilde n, which is the periodically repeating version of the finite length sequence xn. So this is, remember, this is finite, and this is infinite length. Now I take the time reversal over x tilde of n, which means x tilde of minus n. So this is very simple. All things are just reversed. This axis, all these come here, all these go there. So now I have to take the window of 4, and this is the window, right? So very simple. So basically what you ultimately get is the 0th term has stayed constant, this has stayed constant, and they have flipped. flipped. So that is it. So you see this thing has flipped and this thing has stayed constant. Okay, nothing difficult about it, just visualization. You know that it is periodic boundary condition only. Okay, so now let us look at the DFT of a signal of the sequence. How does it change? If the DFT of small xn is capital Xk, then what will be the DFT of the time reversed version of xn? So basically x of minus n. You put the modulo everywhere anyways. So the DFT will be something like this, but let us derive that. Basically simply x of minus k. Let's derive that. So x of k, x dash k, the thing which we want to compute the right hand side. This is simply summation n equal to 0 to n minus 1 x of minus n. This is the thing. You can put modulo n here, no problem. That is by default always there. I can replace this with this. Both these things are exactly same because of modulo n, no problem. Now let m is equal to minus n, right? I think it should be n minus n. Let m equal to n minus n. Why did I do this? Why did I do this step? I did this step because I know that minus n, all the indices will go out of the range because n is equal to, let us say 1, then x of minus 1. I don't want to go out of my range of 0 to n minus 1. To bring back the range to 0 to n minus 1, I do this step. So right, so this is what I have done. Now with the new m, now new m lies within that range which I want, x of m, and whatever is in the numerator, so you know this term will go away because e to the power this thing will be simply 1, right? That's what, right? Now consider this, m goes from 1 to capital N, but I want m to go from 0 to n minus 1, so only one index. At m equal to capital N, there is a problem. Let us consider that index. At m equal to capital N, now you have your x of m will be x of capital N modulo n, which will be same as x of 0, right? So basically you just replace, and then the second term, this term will be e to the power j2 pi k n upon n, which is e to the power 0, which is equal to 1, right? So which means both are same. So you can replace this whole term at m equal to capital N with the same whole term at m equal to 0. So just you can change the limits, m going from 0 to capital N minus 1, the same thing. And you know that since it is a plus sign here, to compare it with x of k, you replace this with minus, and the minus can be absorbed by the k. So this is same as x of minus k, right? Okay, now next concept is circular time reversal. I'm sorry. In the circular time reversal, let us look at some graphs where you can see actually things happening. So I have written a code to take a complex xn, right? My xn is not a real number anymore. It's not a real sequence anymore. It's a sequence of complex numbers. Now the blue parts are the blue dots represent the real part, green dots represent the imaginary part, right? And if I do a time reversal on this, what do I get? This 0 remains same and everything else gets flipped. This is the flipped version of this, right? You can see. Now let us compute the Fourier transforms. The Fourier transform, the DFT of xn will be xk. It comes out to be this if you compute it. Okay, so there is no magic here, just simple computations. Now if I ask you what will be y of k, you can compute it from here, and what you get is, I computed it from here, I got this. So from, you compute here DFT and you compute here DFT, you get this thing. But now you notice that this phi of k is simply x of minus k modulo 5 here, because the sequence is of length 5. So here capital N is equal to 5, right? This is what you observe. Right, the zeroth component stays constant and everything else gets flipped. Okay, now let us look at some more properties of DFT. Okay, let's look at some terminology. Conjugate symmetric. What is conjugate symmetric? This is the complex counterpart of real even sequences. If xn is real, then even means x of n is x of minus n, and odd means x of n is minus x of minus n. But in the complex domain, it becomes conjugate. X of n is x conjugate of minus n, and x odd n is minus x conjugate minus n. Right? If x is even, then this property is satisfied. If x is odd, this property is satisfied. Now, given any xn, a complex xn, complex sequence, how do you decompose it into even and odd parts, which means conjugate symmetric and conjugate antisymmetric parts, right? So, very simple. Just like you do in the real domain, you all remember this probably. X even is basically x of n plus x of minus n, and you average out the two, right? Similarly here you have x of even n, or x of conjugate symmetric n is xn plus x star of minus n. You can verify this. You see from this formula I can say x even n. Okay, let us look at x even of minus n. So this will be simply equal to x of minus n plus x star of n half. If you take a star now, x star of even of minus n, this will be equal to half x star of minus n plus x of n, let's say, which is same as x even of n, right? So this property is true for any general xn. I think you remember this, but just I did it again. And similarly, x odd n can be defined like this: xn minus x star minus n half. This is true in general for any complex xn. Okay, now, okay, this is true for infinite x of n's, but for finite xn, just replace these terms by modulo n. That's a simple change, and then this xe will become xep to signify that this is a periodic boundary condition or a finite length xn with periodicity assumed, right? And xo will be replaced with xop, p for periodicity. That is just a convention, but the formulas remain same, but just that now simple n will be replaced by n modulo capital N, and everything will be done in that way. That is it. So otherwise everything else is same. Okay, these were just some terminology. Let us see if I do these transformations, how do the DFT change? Okay, let us say if xn is a complex sequence, if I consider only the real part of xn, what will be the DFT of that? So the DFT of that will be this. It is an even function or even periodic. Basically, it's conjugate symmetric, and periodicity is just to signify that this is the modulo capital N involved here. Okay, let's do the proof here. So the LHS is simply, LHS is real part of xn. What is real part of xn? It is xn plus x star n half, right? You all know this is how you extract the real part of xn. Now take the Fourier transform. Now the DFT will be, so the Fourier transform of xn is simply xk. Fourier transform of x star n, you have derived it to be x star of minus k. right? Of course, don't forget to put capital N here. That is understood. Now this whole thing we have defined in the previous slide to be x even capital K. Sorry, x even of K. Right? That is it. So that even and odd properties are true both in time domain as well as the frequency domain, right? Because both are sequences of length n only. Okay. Next, okay, so this is proved. Next, we have that j times imaginary part of xn. If you take the DFT, it comes out to be capital X odd periodic counterpart or odd periodic part of x of k. Okay, the proof is also very simple. Let us start with the LHS. It is simply the imaginary part of xn will be xn minus x star n upon 2j. So j and j get cancelled. And then you take the DFT. DFT of xn is x of k, you know. DFT of x star of n is x star of minus k. That also you know. Of course, there is capital N here. And this thing is equal to XOP. It's the odd counterpart of decomposition of XK, with P to signify that this is the periodic boundary condition. So this is RHS, hence proved. Another result for symmetry property: if my X is an even periodic function, then the DFT will be real. The proof is very simple. Let's start with the LHS. You know that this is the even periodic part is simply xn plus x star of minus n half. Now I compute the DFT. DFT of x star of minus n is x star of k, and xn is xk, and you know this is the real part of xk, right? That is it. And similarly, you can prove that for the odd part of xn, the DFT will be j times imaginary part of xk. So proof is again very simple. Start with the LHS. The conjugate antisymmetric part is simply this thing, right? And then you take the DFT. Xn becomes this. X star minus n becomes this, and this is the imaginary part of xk. That is it. Done. Okay, so there is in your book, the textbook Oppenheim, table 2 very nicely explains or nicely summarizes all the properties which we have just now seen. You can go through it in the book and you can prove them on your own. The references: Oppenheim, chapter 8, section number 6. Thank you very much.